Welcome back. We're going to discuss the effect of an added substituent on an incoming substituent. Okay, let's make that very clear. So for instance, let's say, let me get my pen. Okay. So for instance, you must have at least one substituent for this concept to really work. So for instance, say we took our benzene ring, okay, and we added it to Cl2 FeCl3, which is basically halogenation of the benzene ring, and then we ended up with this as one of the products. Actually, only product. You could have other products, but that will be residents of it. So we said that the Cl is the substituent, right? So here I've got something very generic, X. X could be any of the 5 reactions we looked at, right? So it could be any one of the halogens, okay? It could be, I've done the Cl, right? So it could be Cl or F or Br or I. If you chose this to be F2, Fe, F3, etc., etc., or your X could be, it could be NO2, or your X could be, these are some of the substituents we looked at, SO3H, or we looked at, alkylation, CH3, right? And then we also looked at, we haven't looked at phenol. I wanted to reserve that for separate discussion when we talk about alcohols. So these are the 5 major category of substituents that we added in the form of an electrophile onto a benzene ring, right? So the X could be anything. I just kept it generic. Say, so we classify the positions on a benzene ring as ortho, para, or meta with respect to the X that's already there. Okay, so for instance, whatever be the X, okay, the X does not really matter to actually determine the ortho, meta, and para. You must have one substituent, say this is NO2. Okay, with respect to the existing substituent, okay, I'm going to add different colors just to make that difference. So the one in blue, this is ortho. Similarly, this position is ortho as well. Okay, with respect to this substituent, the substituent, it doesn't matter what the substituent is, the ortho, meta, and para is always going to be the same with respect to a single substituent. Okay, the substituent here could be different. We haven't still looked at the effect. We're only trying to learn the positions of the ortho, meta, and para. With respect to this substituent, I'm going to again change my color, get a different color, maybe purple. This is meta. So is this. And last one is para. Let's get a different color. So the black is good. This right here is para. So irrespective of whether it's NO2 or Cl or SO3H, the position ortho, meta, and para is always the same. So you have 2 ortho positions, right? You have 2 meta positions and 1 para positions in every benzene ring given a substituent. Now you cannot really make sense of ortho, meta, and para for a simple plain benzene ring. You must have at least one substituent, and with respect to the substituent, the immediate adjacent positions left and right is ortho, one more step below is meta, and further below is para. Okay, just remember this. I'm not going to tell you on a test which one is ortho, which one's meta, and which one's para. It's just very easy to remember. So something you have to remember. Now, however, you do not have to remember this table. Okay, let's say you have a fluorine, chlorine, bromine, or iodine attached to the benzene ring. Okay, this is the first substituent that you already added in the form of an electrophile to a benzene ring. These are ortho-para deactivators. As you see, the chances of a meta product even forming is only 1%. So we normally don't say that. Say if your molecule is this, okay? If you have added this as an electrophile, then any other incoming electrophile, as we will see, will only go to the ortho or para positions. Okay, this is ortho, ortho, ortho. Sorry, this is para. Ortho, ortho, para. Right? So this is, if you're starting with this, you started with the benzene and then you added a fluorine. If you have a fluorine, chlorine, bromine, or iodine, these are deactivators, and whatever incoming nucleophile would only go to the ortho and the para position. Okay. Similarly, say you started with benzene, and then you've done a Friedel-Crafts alkylation, and say you added a CH3. Okay. This is also an ortho-para directing group, but this is an activator. Okay, we'll worry about the activator and deactivators at a later time. But for now, let's just focus on, okay, this is also ortho-para directing activators, okay, because these are electron deficient groups, these are electron rich groups. So these are activators, these are deactivators. But the point here is any one of these groups, okay, will direct the incoming nucleophile to the ortho position or para position. Okay, now let's say we also did NO2, right? Say you have NO2 as your starting electrophile. Now, if you add another group onto this ring, it would only go to the meta position, not to both meta position, one of the two meta positions, okay? Because these groups are meta directing groups, okay? Do a little cleaner job there, okay? These groups can only direct an incoming group to a meta position, see? So you do not have to remember it. If you can figure out, if you already added an electrophile based on this list, you can see. Now you also have to look at something. Let's say you have a fluorine and you have an incoming another substituent that you can add it to either the ortho or para, but you see that in all the cases the para position is more stable than an ortho. For these type of reactants, okay, you see the percent of ortho versus percent of para is always higher. Okay, that's usually the case for most, except for this one, which is the opposite. But typically speaking, most of the time, your para product is higher in proportion over your ortho. Okay. For single digits, we normally don't even care. It means meta is rarely formed. Okay. So here, same thing. You see that the meta product is the only major product, okay, most of the time. So I won't ask you, subdivisions of products. I will ask you just a major or minor. So if your substituent is NO2 or CN or one of the other new electrophiles, we haven't learned everything, but we did learn, we have learned these. We have learned these. Okay, these are the two we have learned so far. So if these are the two electrophiles sticking on the benzene ring, that means that if you add an extra group, it would only go to the meta position. All right. Let's look at this. Say I have already started with my benzene. Okay. What I have here is the product from this reaction. Say I've added my benzene to methyl chloride and AlCl3, and I have made this as a product, right? This is what we learned in the previous sequence. Now this, when it reacts with HNO3, H2SO4. Now if you remember from the table I showed you, if this were to be the electrophile attached to the ring, it's an ortho-para director, right? And the para or the ortho product for this particular case, the ortho was the major product and the para was the minor product. Okay, so that means the nitric acid and sulfuric acid, you know, if you remember the electrophile reaction, this would produce NO2 plus, right, as the major electrophile. That's all you really have to remember. Then you can call the other one as just base. Okay, so NO2 plus reacts with the benzene ring. Now it can go to the ortho position or the para position. So we will have two products. So this will stay where it is. With respect to this, this is para, so the NO2 will go there. Or you don't have to write both ortho position, write one, either the left or the right side. You don't have to do both. So I'm just going, I always do my right side. Okay, so this is the major product. This is the minor product. Okay. So we're combining two reactions now. This is a reaction on its own when we studied alkylation. This is a reaction on its own when we studied nitration. So if we already have an alkyl substituent, then the incoming NO2 can go to the ortho position or the para position. So this is the ortho, this is the para, right? This is also ortho. You could have added it on this side, but I always prefer to add mine to the right. You can add it to the left side. It doesn't matter. Okay. So that's how you do your ortho-para directing. I have two more compounds, but in lieu of time, I'm going to stop this video here and then redo a couple more examples on a separate video. All right. So stay tuned.